Fantastic. Cool. Can I start? Yeah. Cool. Hey, welcome here. We will give a talk today called Rollups Broke Ethereum, but we're here to fix it. And it will be a joint talk between myself, Friederike, and Jordi, the founder of ZisK, and Edu, who will give a demo. So the way that this is going to work is I'll explain what the problem is. Jordi will give you the solution, Edu will do a demo, and I will talk about what this now enables to end. Okay, let's talk about the Ethereum dream. Ethereum was never just about a blockchain, right? It was about what happens when you make a computer truly permissionless. Anyone can deploy code, anyone can use it, and once it runs, it just runs. So you don't need to be a bank to kind of launch a financial product anymore. You don't need to be a broker to distribute it. You don't need to register a company to coordinate capital in some way. You just deploy a smart contract. And the way that this was achieved was not by removing the infrastructure. It was by making the infrastructure truly neutral. So something that belongs to no one, belongs to everyone. And that was the secret behind the success of Ethereum. And once the infrastructure becomes completely neutral, something else becomes possible. In Ethereum, smart contracts, they don't live in isolation. They can talk to one another. So kind of, you can have, say, an oracle, a stablecoin, a money market, a DEX. And in isolation, they are all somewhat useful, but the real breakthrough moment happens when they can connect to one another, when they no longer live in isolation. So once they can build on top of one another, plug into one another, use one another, what you actually get is a composite system that is much, much more than the sum of its individual parts. You get a composable, infinitely expansible financial system kind of to boot. And this was wonderful. And then, oh, you can't actually see my slides. Sorry. Okay, fantastic. Can we fix this? They can't see my slides. They can't see my slides. Okay, I'll just go on talking. And, oh, there we go. So kind of, there were slides before this, but kind of like, okay, so once everything is neutral, everything can connect to everything else. It was wonderful, and then we broke it, okay? There was a reason for breaking it. What was that reason? So the reason's in this chart. So if you actually look here, what you see is the average transaction fee on Ethereum for the 7-day rolling average. And you can clearly see that demand went up. So kind of you can see the ICO boom in 2017, 2018. You can see the DeFi summer. You can see the NFTs. But what's even more notable is look at how it came down again, okay? So there's a reason why the average transaction fees came down again, why they're no longer $50. And this is the reason. So look at the number of L2s kind of on the same timeline. So we got the first couple of L2s experimental 2020, and today we have hundreds of L2s. Every 2 weeks, a new L2 launches. And what that actually did was it moved the execution largely off mainnet, okay? So kind of execution now majorly happens on L2s. This means kind of the transaction cost has come down a lot again. We solved scalability, but we did it at the cost of the composability that we had beforehand. So kind of L2s don't talk to each other well, you know this. This is what we're here to solve. And in this chart, this kind of drives it home how we actually got here. And then the question is, okay, how do we now go about fixing this? The core problem is that when you're on a blockchain, kind of the blockchain has a perfect understanding of what its own state is. It has absolutely no visibility into anything that happens outside of itself, okay? So in order for the blockchain to kind of interact with another chain, it needs to understand what the other chain is saying and needs to verify that what the other chain is saying is actually true. And if you want to do that at the same time, if you want these chains to kind of synchronously compose with one another, you have to do it not eventually, you have to do it right that second. So the way that chains kind of check the other chain's state is typically done by so-called zero-knowledge proofs. So a zero-knowledge proof is a proof that a computation was executed correctly. And by that I mean that a specific program acted upon a set of inputs and yielded a specific output. In the blockchain case, the program is the state transition function, the set of inputs is the previous state, and the new transactions that you're having included, and the result is the resulting state of the blockchain. And until recently, constructing these proofs took time, okay? So verifying the proof once you had it was always fast, but constructing it was very much not, okay? So, and this is where the innovation that underpins the easy comes in. We use zero-knowledge proofs that are real-time to have one network prove to another network the state it's acting upon. So let's deep dive into the architecture, and I hand over to Jordi.
Thank you, Friederike. Yeah, to learn a little bit, because this looks like magic, how this is actually possible, and to understand a little bit how this works, we need to have maybe a higher overview of what's how we understand blockchains right now. Okay, so at the beginning, blockchains, I mean, Ethereum just it was consensus about an execution and put it in a chain. Okay, but today we have this idea of splitting data and execution. So modern blockchain is just data. I mean, it's just a ledger where you can put data there. Okay, and the queries, I mean, when you are executing, when you have this ledger, this data that's fixed, we can do queries to this data. Okay, and actually the result of these queries can be used to use these queries. Okay, and this data, it goes together with a proof that actually verifies that this data is correct and this computation, this view of this data is the right way. How this apply, for example, normal blockchain? Well, these data are the transactions. We can see if you take all the data, all the transactions, just the raw transactions of Ethereum, and you put take off the block, this would be the data. And then we have, I mean, we can have a deterministic program that actually processes all this data and computes the current state. Just processing, of course, all these transactions. If you had to do that, like every block, this would be very expensive because we would have to go to the history of Ethereum and process the thing again. But the cool thing of ZK and recursions in today's days is that we can do recursively. So actually we can take the result, so we can take the current state of this block, new data pairs, we do a new query of the result of new state of this data, and then we get a new proof. Okay? And we can do that forever, okay? And we can understand this like a database and then with a query. Okay, and how this applies to synchronous. I mean, when we are how this applies to rollups. Okay, to synchronous rollups. Well, synchronous rollups, Just to be clear, I mean, synchronous rollups means that you have one smart contract in one chain, and you can do a call to another smart contract in another chain in the same transaction and get the result, and maybe calling another smart contract in a different chain, or even a nested call. I mean, this different chain can call you to something happen in L1. So you have like a normal single Ethereum. So, but this happens in the same atomic transaction. So you're just doing one transaction in one chain, and this is calling to the rest of the chains. Okay? So how this works? Okay, imagine that you have all the transactions of all the blockchains, of all the rollups, okay, in the data. We can process, I mean, actually we can do a deterministic program that actually process these transactions, process all these cross-chain transactions, and we create a proof that the state, or in this case, the states of all these chains are correct, okay? So composability between rollups and thinking on this model is quite straightforward, thinking in this way. Okay? Where is the problem? Okay? Well, the big problem is here when we are talking about L1 and L2 composability. Okay? So if we have only L2s, that looks quite easy. Well, it's not that easy because you need to create these proofs. Okay, so you need to get transactions of different chains and aggregate them, so decompose them, and actually compute this new state or these new states. Okay, but it's actually doable, assuming that we are able to create these proofs really fast, and we will see that actually this is possible. So let's go to the main topic. I mean, how we connect L1 and L2. We want to create a system where people can deploy rollups of any kind and should be able to call an L1. Or the other way around. I mean, if you're calling from L1, you should be able to call an L2, and the other way around. So how this works, okay? So let's go through an example, okay? This it's not a trivial example. It's a little bit complex example. But imagine that we have a user in layer 1. We want to call a DAO that's in the layer 2, and maybe the DAO is calling back to some whitelist, I mean, who can vote or whatever in the layer 1. I mean, it's just an example, but gives you how this would work. User R would call the DAO would call the whitelist may return if this user can vote or not. They would execute the vote in there, and then finally return the result in user A, which maybe just pay some fees or whatever. Okay, so this is an example. Okay, so how this would work? Well, the first thing that we do is how do we emulate the calls, because we don't want to build a new Ethereum. I mean, this should work in the current Ethereum. Okay, so how do you call to a rollup, to a smart contract that's in another chain? Well, here we introduce this idea of a proxy contract. Proxy contract is when we have a DAO that's running in the layer 2. Actually, what we do is we build a contract that's the representation of the DAO in the layer 1. So the idea is that if you are calling to the DAO, is equivalent, is the same. I mean, this is a way of calling the DAO in the layer 2. And the other way around, I mean, if you're doing a transaction in layer 2 and you want to call something in layer 1, contracts in layer 1, they may have a representation in L2. So doing a call is just doing a normal call. Of course, the address, it will not be different, it will not be the same, but it would be a deterministically computable. I mean, it would be one representation of the other. We can compute, we will see in the demo how this works, but it's just a representation on the other. Okay? So, and then how this would work, okay? Well, if you see the execution here, actually, I mean, you are starting from the beginning, you are your user A, the user A call something to the layer 2, the layer 2 is calling back to the layer 1, the layer back is returning to the layer 2, and the layer 2 is returning to the layer 1, okay? So we have like two chunks that are happening in layer 2 that are not executing in layer 1, they're executing in layer 2. So what we do, okay, let's build a table. Actually, what we do is we build a table of these executions that happen outside the chain, outside the layer 1. The table is the one that we see before. And this table, what says? Well, it says if the rollup 1 is in the state 0x1111, and you do a call with these parameters, the new state is going to be 0x22, whatever it is, and the result would be a result, or in this case, it would be another call. So you'll have to do another call. okay? And the other way, so if I'm in this state 0x2, in 0x22, and I do a return, so I return the call, then what happened is that the result of this, the new state will be this, and we return this one, okay? This table, I can just build this table. I can build a zero-knowledge proof of all these transitions, of all these actions that happen outside L2, and prove that they are correct, okay? And I can push it, so I can have machine a transaction that happens at the beginning of each block, where I put all these executions in the other layer 2s, proven executions that happens in there. So how this would work? Well, when the user A is calling to the DAO proxy, in this case, well, the DAO proxy, what we'll do, we will do a lookup to this table. It will check that the current state of L2 matches with the current state of L1. It will apply the new state. So this is equivalent to executing the transaction, because this is deterministically what happened, and will return what actually was proven, that when you this call returns. Okay? In this call, it will not return. In this call, with what we do, it will do another call. So it will do another call to an L1. The L1 will execute the code, what happens in L1, okay? And at some point will return. And the return, I mean, this proxy smart contract will take this return, will look again to the lookup table. It will take the second and say, okay, if you apply a return, the state changes in this way, and then you return back to user A. So actually, what you see, what the user sees in the layer 1, it sees a synchronous call that happens, and the call is happening in both sides because you are updating in L1 the state of the L2. So this is the main idea of how the system works. Okay? So how this would work a little bit in a practical way? Well, the practical way would be we call it a composer. It's like would be like part of a block building. So in an L1 block building, actually you will take all these transactions, we'll compute all these things, you compute all the proof, and what are the steps that we'll do? Well, maybe in the first step, maybe we'll create all these proxy contracts that you need in this execution. The second part, you will create these state transition functions. So all these executions that happen outside, you will create this table, compute, of course, the proof, which is, you will see that's the critical part. We'll put it on chain, okay? But this is just store on chain. Then we will do the actual. Executions. We'll do the executions, and these executions, when they are calling the proxies, they will emulate these calls, so everything will happen. Okay? And maybe finally, of course, there are rollups. So if there are transactions that don't touch L1, I can just, with a single state transition, I can process many transactions at a time. And this is how Rollups scales, when you are doing transactions that don't affect L1 in this case. Important to say that these transactions can be L2 to L2. That can be really fast too. But this is a little bit for another day. Okay? Things that I want to highlight here. Okay? Rollups, they don't need to be EVMs. It could be native rollups that they follow the rules of EVM. They cannot change it. They can be very native rollups. But this system allows you to create any chain, maybe a WASM EVM, or maybe a DApp chain, or a privacy chain. So we will see a lot of examples, but it can create any chain. The only way that, the single way that connects is via calls. So this chain needs to support to receive some calls, or maybe to do some calls to L1 or to the other chains. And I think this is something that's very useful because this allows the people to extend Ethereum. So Ethereum is not going to be fixed to maybe an EVM. Each one should be able to create in a permissionless any chain and run and execute it, and connect all these in a synchronous way. One word about preconfirmations. Is orthogonal to the system. You can build preconfirmations in L1. This would help a lot. This will help latency. This may help a lot, but you can build the system without preconfirmations and still and still works. Okay? Just the last things. So here we are creating this EEZ. I'm very excited on that. And the main enable is the zero knowledge proof. This is what we have been talking here. In the last month, I'm talking the last month, literally, this has advanced a lot the performance. Okay? So in ZisK, ZisK, we are able to prove blocks in real time. And of course, with all the security, 128-bit security, quantum compute, quantum resistant, we are fully open source. So we have been working, and we are very committed to keep working on that part. Zero knowledge proof is very linear. It's very linear in, it scales very well. I mean, if you want to prove more transactions, you just put more hardware, okay? And it scales very well, okay? Where is the point? I mean, the critical point, and this is where in ZisK we have been working a lot, and we still have some margin to improve, but it's working a lot. So in the case of synchronous composability, so when you are building a block, it's okay, you have this block building or the composer part, okay? So you are building the block naturally. But you need to build the proof. So actually, you probably will start building the proof at the same time that you are already building the block. So you kind of pipeline these things, okay? But the problem is this gap. I mean, when you are finishing of building the block, I mean, what's the time that you have the proof available? This needs to be very fast. If it's less than 12 seconds, then you will miss the block, okay? So currently, we are around 3 seconds, even less, and we have margin to improve that. And this is what really enables this technology. I mean, this it's not only the way that we can scale the quantity of transactions by just putting more GPUs, is that the latency of finishing these proofs, so of having this proof in real time, I mean, just when you finish to build the block, having the proof, this time is the critical one, and this is where in ZisK we are already there, and we have still some margin to improve. Okay, so now I just give the word to Edu to do a demo about what we are already building right now.
Wait. So maybe I need some help here. Okay, no, I'm fine, I guess. Yeah, I don't know. Sorry. Can you help me here? A second. No. Here. Okay. It's fine. Thank you. So hello everyone. I am here just to try to make a demo and try to put some light to the explanation that we just got from Jordi. So my intention is to make this real. So first thing first, what I'm going to try to do today. So in one side I have an L1, and in the other side I have an L2. So mainly the idea is that I want to make an atomic transaction between both chains. And I have a very basic example, a hello world example. So mainly the idea is that I'm going to try to exchange a word between L1 and L2. Yeah, that is the magic thing that we are going to try to do today. So I have 2 browsers. I have Chrome using or connected to the L2, and I have Brave connected to my L1. So the first thing is to deploy a contract in L2. That is the first step that we need to do. So for that, I'm going to try to ask a word from the public for that. Any suggestions? What word I should use here? Sorry? Gnosis. Okay, let's do Gnosis. Why not? Okay, so as you can see here, very basic smart contract. The constructor set a word, and I have a function that is get and set a word. That's it. So now let's deploy this on L2. So yeah, that's it. From the point of view of L2, that is all the thing that I need to do. I only need to deploy a smart contract. Now I only need the address of this contract on L2 in order to be able to use that on L1. So now we have this address, I mean, we have the transaction here. Okay. Okay, so yeah, we have deployed a contract. Nothing crazy here right now. So now it's time to move to L1. Yeah. So here is this remix is connected to L1. So the first thing that we need to do here is to deploy a proxy. As Jordi has explained it, a proxy is a representation of a smart contract in another rollup. So now I need to deploy this proxy in order to be able to communicate L1 and L2. I am deploying because of, I would like to explain that, but theoretically we can do that behind the scenes. So it's more about to explain how this works. So for that, yeah, I need the API, and then I need to connect to the Rollups contract that we have deployed on L1. Mainly this contract is in charge of posting the batches, creating the proxies. So yeah, let's connect to this contract. So here I have a function that is create cross-chain proxy. Mainly it takes two arguments. It takes the original address, the one that I want to use in L2, and the rollup ID. In this case, I only have L1, and I have just one rollup, so the original rollup ID is 1. Then I need to get the address from L2 and deploy this proxy contract. So yeah, the thing is, what we have done so far, again, we deploy a contract in L2. Now we are deploying the proxy on L1, that is the representation of this contract on L1. And at the moment that I have this proxy, like now, I can start to use it directly, this proxy, on L1 on my own contract. And that's the next thing that we are going to do. So here, yeah, we have the address of the proxy. So now, time to do the real thing. We have another basic, very basic contract on L1. Mainly, it's a function that I set the proxy that we are going to use. We give a word, because as I mentioned, this is an exchange of words. Mainly, the thing that it's doing is calling the proxy to get a word from L2 and set the new one into L2, and just print the message. So let me deploy this contract. Okay, 1 second. I think it's compiled. Yeah. So, okay, let's deploy it. And yeah, and now we have everything. We have the L1 contract calling a proxy in L1 that is the one that is going to move this information between L1 and L2. So now I am ready. I can, okay, let me close this. So now I need to set the proxy address, that is this one that we just deployed. Or, hi. So let's send the transaction. So what is happening here is mainly what Jordi has explained it. So we send this transaction to the composer. The composer is simulating the call from L1, move to L2, go back, and finally go to L1. And if we settle everything at the same time, is when the magic happens, and something atomically can happen between both networks. So as you can see here, let me see. Let me open in the browser. It's easy to see. Oh, we have it here. Coming message from L2, Gnosis. Let's make it easy. Yes, that's the magic. So a little more explanation about this, just to give a little more light on your explanation. So this is the transaction. Oh, sorry. Okay. Okay. So this is the transaction that we just did. This is the block, and in the block we have two calls. We have the hello L2 wall, and we have the post batch. if we take a look to the batch, here we can see like we are performing L2 execution, and also an important part is that we have post a batch with all the state transitions that are happening in L2. If we consume an entry on L1 and it matches with the batch that we just posted, is when we can make all the things happen at the same time. And here, I mean, it's hard to see, but you have all the table, all the entries, and this is atomically happen or not happen. And yeah, this is the magic that is behind EC. Yeah. So now
it's me again.
Yeah.
Okay, let's present this. Oh, here we go.
Yeah.
Fantastic. So what you just saw changes what's possible. So kind of you saw a fundamentally new primitive. Kind of you saw edu demo a cross-network call return a response in a single block. This is fundamentally new. And if you look at kind of what this now enables, is it restores the composability between different networks that we lost when Ethereum scaled via L2s. So you get to keep all the benefits of the scalability, but now you can compose again like you could before we had the L2s. Let's look at a couple of examples, because I understand this was really high level. Let's look at bridging. Okay, so today, say you have USDS on network 1, you want to send them to network 2. What you do is you go to the bridge contract, you deposit your USDS, you lock them, then a message is generated. The message is passed to network 2. There's relayers, finality, proof generation in the background, so you wait. Then your tokens on network 2 become claimable. That doesn't mean anything yet, so kind of it means a smart contract on the other network owes you tokens, so you go there, you claim the tokens, and then you have the tokens on the other network. That is how bridging currently works. In the Ethereum Economic Zone, what you can do is you can just execute a transaction across both networks. So you touch both states simultaneously, and it's as easy as sending a token on the same network. Okay, so example 2, liquidity. Currently, you have the same pools deployed on many different networks. Okay, so here you have an ETH USDC pool, and you have it on chain A, B, and C. They have different prices. The liquidity is fragmented. And kind of arbitrage is kind of what barely stitches it back together. In the Ethereum Economic Zone, however, you still have all of these various pools on the various chains, but they stop behaving like separate markets. They become a single market because while the pools are still on the individual networks, your transaction can actually touch all of them at the same time. So the liquidity is global, despite the fact that the pools are local. And if you have dApps like CowSwap, they see where all the liquidity is across all the networks in the EEZ, and they find the best way to kind of settle your trade. And if the liquidity for the token you're trading is better on another EEZ network, kind of it routes it via that network and then kind of loops it back. So kind of it all happens under the hood. You don't actually have to know about this. It just ensures that the EEZ becomes a single market again instead of a number of loosely coupled markets as we currently have. Okay, I'll give you more examples. I hope you're ready, okay? So next example is composable finance. Say I have Ethereum, I have ETH on chain A. I want to stake it on another chain. Then I want to borrow against it on another chain, and I want to use that liquidity I just got on another chain still, okay? Today, this is a bunch of steps with bridging in between. So kind of you have a delay and a failure risk at every step, and it'll take you a long time. In the Ethereum Economic Zone, you can touch upon all of these states in a single transaction. So all of this can happen in a single block. And the way that this happens is not by moving the infrastructure from chain to chain, it's having these composable calls that can touch on all these different states and change them in a consistent manner at the same time. Cool. So far, we have looked at things that kind of speed things up or kind of make things that are subsequent in nature kind of faster or more secure in some way. It also allows completely new mechanisms. So for instance, say you have a protocol like Aave, okay? Today, Aave is deployed on many different networks, and the Aave deployment always sees the tokens that you have on that network, and you can borrow against them, okay? So it's capital inefficient because Aave doesn't see your entire balance, it just sees what's on that network, and then kind of you can borrow against that specific collateral. In principle, kind of as soon as Aave understands what the state of the other easy networks is, you can now borrow against your one collateral base, and whatever kind of, if you're underwater, you get liquidated, but kind of it's all possible because it's synchronously composable. Another example. Today you have a safe. So safe is deployed across 300 EVM networks. So you have a safe, and you have associated safes on various other networks. Today they are independent, so kind of the configurations of these safes, they can be different, and kind of if you change the configuration of one safe doesn't mean anything at all for the other safes. So kind of you get state drift in between your configurations. In this new Ethereum Economic Zone, what you can do is you can designate one of your safes kind of the lead safe, and when you rotate a key, for instance, it rotates them automatically on all your other 300 safes. Or kind of, if you set permissions, the other 300 safes can follow. Okay, but it goes much further than this. So kind of on the safe, in principle, you can do this manually. It's not very convenient, but kind of you can do it. Synchronous composability also allows things that we genuinely do not have today. Okay, so you could have your identity, your private identity on a privacy-preserving chain. It doesn't have to be EVM, because as Jordi said, this is all call-based, so kind of you could have it on Aztec or wherever you like. And you can verify yourself against the contract on another chain by virtue of this private identity. So your private identity never leaves the privacy chain, just the proof that kind of you are granted access because you fulfill membership criteria, your reputation is enough, or kind of you have the credentials. Just the proof as to that leaves the network and then allows you to access, say, a file-verse document on an EVM chain. And so kind of while kind of your capital kind of becomes global, so does your identity. You no longer need to replicate your identity across every single network or kind of use a trusted third party. And this doesn't only apply to public networks. This also works for private networks, okay? So if you have a Prividium, a private chain that is ZK proven, then you can have it interact with Ethereum and public apps on Ethereum, okay? So when we talk about Prividiums today, we often actually mean banking consortium chains and so on. And I mean, obviously, this is also a viable use case, but I can also see a future where, for instance, nation states kind of deploy their own Prividiums, okay? So kind of you have, say, you're the German state, kind of like you want to issue your citizens with an on-chain identity, but you don't want to do it on a public chain, right? Kind of like you want to have the validators be, I don't know, the branches of the federal bank or something. But kind of in order for that to be useful, it needs to be able to compose with public chains, because by virtue of it being a private chain, there's a private permission chain, there's not going to be a whole lot of interesting things on there, right? So kind of you give your own citizens a way of having a trusted state-verified identity on public networks. I can also see states issuing CBDCs on these kinds of chains or T-bills. So this is really large concession. So kind of for kind of becoming a part of the EZ, what's not important is that you are EVM or public. What matters is that you can prove your state. If you can prove your state, you can compose. So this isn't just theoretical, okay? You just saw Edu give the demo where he called from a contract on L1, he called a contract on L2 that gave him a word that you gave him, namely Gnosis, and then kind of it reverted back to L1 and kind of completed the loop, kind of yielding this entire phrase. So kind of you have seen that it works. And it's not just us, so Gnosis and ZisK pushing this. It's a community effort. So there's a whole lot of ecosystem players who are on board here. So kind of all the major block builders are on board. That's Titan, Beaver, and Flashbots. All the dApps that you have seen. So so Cow, Save, Aave, Spark, Monerium, Xstocks, and so on. They are all founding members of this. This will be available from day one, and mainnet will be pretty soon, sometime this summer. If you want to learn how to use this for your dApp, if you want to learn how to connect your L2, if you want to look at the code base, look at this, come to our website, eez.io. And thank you so much for coming to our talk. If you have questions, you have to go outside, but we'll be there.